Well, hello friends. Today we are going to continue with the profiling stuff from yesterday. So if you didn't see that already, yesterday we built a simple sampling profiler into the kernel. And let me gather a profile of something. Maybe we will, I don't know, do some painting here. And let's see. So we have paintbrush. PID 16, so we'll say profile 16 on. Then I will draw some happy lines here. Hello, friends. All right, and we'll turn off the profiling. And we should now have a big profile in proc profile that we can fetch. So these are all of the samples that we took of the paintbrush process while I was painting into it. So what we're going to do today is we're going to take this sample and we're going to store it somewhere, and then we're going to make a little program that allows us to see the profile as a tree, like you would normally see in a profiler. So we will collect all of the stacks and then put, like, I guess, the root stack as the root of the tree. So the tree will start with this one, and then if you open it up, you find this thing, you open that up, you find this, and so on. And we will let you, drill into the different stacks so you can see where the process is spending its time. And of course, if you're not familiar with how sampling profilers work, just a quick recap. At a regular interval, we wake up and we see what the process is doing. And basically the way we do that is we just check the current call stack that the process is executing at, and we save that. And then we do that, in our case, we do it every 1 millisecond while the process is running. So 1,000 call stacks per second, basically, if the process is running. So it wasn't running all the time while I was doing this. It was doing, other processes were running, obviously. So it's not going to be like, it's not going to be thousands of call stacks here just because I was recording for a few seconds. But we do capture when it's running. So we're going to be able to see what the app was spending its time doing. That's the point. So anyway. Check out yesterday's video where I was building the profiler into the kernel if you're interested in how the mechanism works. But today we're just going to build a visualizer for the data that we've constructed here. So apparently I can't talk and type at the same time, so we are just going to do it this way. pbrush prof, something like that. .prof, it's a cool name, right? And let me just see that. Yeah, it still works. Check this out, by the way. Tab completion. That was it Will who made that? Jesus, I already forgot. It was Will, right? Yeah, Will was working on this. And we already had tab completion for the commands, but now we also have it for other things, like things in the current path, in current directory, rather. And there's even more things coming soon. But anyway, that's not what we're here to talk about. We're just gonna extract this little file because I want to make sure that I keep that profile around, so I don't have to re-record it every time. So I'm just going to extract it from home and on pbrush prof. I'll save that in my home directory here. That way we'll always have the file. Okay, so now let's build ourselves a little profile visualizer. Now, what are we going to call this? This is definitely a dev tool, and in the profile viewer, that's pretty good. profile viewer. Boom. Nice and straightforward, just like all the other things in this system. Okay, so what do we need here? I'll just take a makefile from some other project here. And profile viewer is going to be the app name. And we'll add it to the make script. Profile viewer. And of course also to the root file system construction machinery. Profile viewer. And I'm going to be lazy and add myself a little shortcut because I like shortcuts. PV. All right. So now we're going to need a main CPP, and let's just start with that. And I mean, I know I'm going to need some model, like a tree model, to store the profile in. So I guess we can make a profile class maybe, and maybe a profile model. And I think that's maybe good. Okay, so profile viewer, sync and run. Okay, profile viewer main. So let's build ourselves a little app here. Starting with a G application. And that's, oops. That's good. And then here we are going to want to have a G window, and we're going to want a G tree view. And I think we're not going to get very fancy right now. We are just going to load it up, put the profile into a tree view, and just let you view the profile. That's really what's 80% of what makes a profile interesting, is being able to browse it in a tree view. And then the other 20% is like, you know, show me only this time range, or invert the tree, show me the various ways to manipulate the tree, like collapse this function into its caller and stuff like that. But that's like this very 80-20, you know, like just getting a tree up on screen is going to do so much. So let's focus on that. So let's do Windows show, set title, profile viewer. And I think we'll take the thing on the command line here. So we'll say if RC is not to my friend, you are in the wrong neighborhood of usage. Profile, profile, yeah, profile file, profile file. Good, because we're gonna need stdio, and that's RGB 0. All right. And then we gotta load this puppy up. So we'll grab C file from libcore because it's comfortable. RGB1. Read only. And if we can't open it, well, unable to open feature error Fa-cha. argv1 and file error string. Return 1. All right. And I gotta redirect that somewhere. There we go. Okay, and then now we're just gonna, so our profile is full of JSON, right? So pbrushprof. That's this guy right here. All this JSON. So we're just gonna load that up. It's one big array of individual samples in ascending time order. So the first sample captured is the first one. So we're just going to load it up. We'll say JSON value, or maybe JSON is, let's get the JSON classes. JSON value, oops. And JSON object. All right, not you. From string file read all. Would probably be nice to have a way to parse JSON incrementally instead of having to read the whole file and then parsing the whole file. It would be nice if we had a chunking parser or something, but right now we don't, and it's not the end of the world. But if you had, say that you had like a gigabyte of JSON, right? It would be nice if you didn't have to load it all up in memory to be able to parse it. Okay. So if JSON is array, if it's not an array, then we'll say, well, invalid format. It's good enough for me. Not a JSON array. Then we are going to include our profile.h. And actually, maybe this should have all gone in profile. So let's make a class called profile. I guess here we can put all the JSON data, so we'll store it in a JSON array. And we can move those up here. That's kind of nice. Don't have to look at those. And then maybe we will do something more like profile is profile, load from file, should be 1. If no profile, then fprint stder unable to load profile. argv1. And we'll need maybe some own putter. Static on putter. Profile. Load from file. Const char path. Not const char. Geez. String view. Okay. Okay, and then we'll have a private constructor. And I guess this will take the JSON array. Probably have a public destructor. Okay, and then here we'll just return. Okay, and then we can move all of this gunk into profile. We don't have to have it in main, which is kind of unsightly. Okay, so profile. Wait, I didn't want path here. I wanted JSON array. Okay, profile. And then we wanted the load function, so onPutter profile load from file. There we go. Now nullputter. I think or no, hold on, this is good so far. I'm just moving stuff around, tidying up. Okay, so cfol construct with path instead of argv, and here we can't just print like that as to be an error. We can't do string view because string view is not always null terminated, so this is a bit sad, but we're going to do this. Make sure it's null terminated. Okay. And here we will return make profile. Or auto profile. Profile is make profile. And JSON, because it's a bit annoying, but like I can't call the private constructor of profile using make, because make is an external helper. So it's just I'm gonna have to make one and then assign the JSON to it like this. But whatever, it's not the end of the world. Wait, are we able to do this? No viable overloaded that. Oh shit, it's JSON as array. There we go. Maybe we can move it like this. Will this work? No. It's private still. Alright, well then, screw using make. Let's just onPutter profile, new profile, whatever. No known conversion from const JSON array. All right. Wait, isn't this how this works? Oh, you have to pass adopt. Oh shit, okay. Okay, well, that was unnecessarily messy. Can we use the move? The R value reference type then? No, we can't. All right, well, let's just ignore it. It's just a copy, whatever. Not every copy is worth spending forever on avoiding. We're just gonna live with this right now, and we'll do better in the future. Leave a little bit of optimization work for ourselves. Once we have a profiler, it will be so much easier to optimize stuff anyway. Okay. Of course, it's not really meaningful to start it up, so we are just gonna keep working on this. So we want to produce a tree model here, so we're going to say profile or G model, I guess. Include. What are we going to include for this? G model. So we'll have G model, and we'll also have a profile model. Oh, okay, and then I think we're going to store in the profile. So now we got to think about what are we going to do with all this data, right? So maybe we can open this up in a web, what's it called, Pluma? I need a JSON viewer so we can look at the data. Come on, Firefox, don't be this way. I know it's hard to be a browser, but come on, man. How about one of you guys? Oh, obviously the stack.who. Gotta go with the Hungarian option. Got a lot of Hungarian bros, so so let's see. This is the data we're working with, right? So actually, the 0th entry in a stack is the top of the stack. So we want to be starting at the last entry in each of these sample. Wait, hold on. Why is this called samples? It should be called stacks. Or samples? These are not samples. These are stack frames. So this is a stupid name. procfs profile. Samples? That doesn't make any sense. It's the frame array. Frames array. Frames. Silly. Okay, so let's fix that right away. Git add file system procfs. Rename frame samples in proc profile to frames. These are stack frames, not profile samples. Okay, good. I got that out of the way, and we can. I think my computer lost his shit there for a moment. Everything froze, but we should be back. So let's just rename this in our file right away. So place home anon pbrush. We'll replace what was it? Samples with frames. Okay, and wow, these programs don't like dealing with this long text, it seems like. Anyway, all right, so we got frames. That's better. So we're just going to start at the bottom of each sample's frames array. We're going to start at the end of it and make that a new root in a tree. And the tree can have multiple roots in the case where some samples start at different roots. I guess that could happen. So we'll allow it maybe, but let's see. How do we do this? We need to store a tree of objects here. Let's see, how should it look like? Profile tree node. That's gonna be a struct. So we have for one frame, we're gonna have the symbol name and the address. String symbol. And U32 address. And actually this offset here, plus 94, maybe we should have put that in a separate thing in the kernel. We can just count them as individual symbols at the moment, but later on we should probably count them the same. But right now, let's just count them as unique. So we'll count this by address, I think. That will make sense. So we got to make a profile tree, and this will have roots. So these will be the roots here. Profile tree node, roots. Maybe we can call these profile node. And a profile node would have children. I feel like that makes some sense. Maybe these should be heap allocated. So we'll just use ref putter for these. We'll just simplify things a little bit. Public ref counted profile node. I'll just turn this into a class real quick. Privat. Explicit profile node. Symbol. U32 address. Okay, and then static non-refer profile node to create const string symbol. New profile node with symbol and address. All right. So what else? We'll get some accessors in here. And we'll need to add children. So this will be just a simple one, just add child. Profile node. Child. And then here we'll just say children append child. Child set parent or parent is this. And we'll have a profile node parent. And if child parent is this, return assert child has no parent. Child parent this, append child. All right. So I guess we can probably create the tree here as well. So now we have this JSON array sample or samples is JSON as array. And samples for each sample. Okay, And then here, now we are going to have the, this is the object that we're getting, one of these. So we have PID, TID, timestamp, and frames. And we just care about frames. So frames is sample as object, get frames. And frames is an array. I guess we can start like this, because as object, get frames. What will that give us? A JSON array, right? I think we'll have to do this. Frames value as array dot for each frame. Frame, and then frame is one of these, address and symbol. It's an object with address and symbol. So auto symbol is frame dot get as object, get symbol as string or null string. And this one is address as U32. Now what are we going to do with these guys? We are going to actually, we wanted to iterate these backwards. So we're already getting off in the wrong order here. So let's see, frames, auto frames array. Okay, so this was what I was getting at here originally. Frames is frames value as array. Frames size -1. Minus I. Okay, now we're going to iterate this pupper backwards. Frames at I. Okay. And now we got to know which profile node we are at. That's going to be new when we start it every time here. So node, starting at null putter, we don't have a node, so we'll start at the root. I guess it'll say if no node, then if no node, then node is find or create root with symbol and address. What's that function going to do? Find or create root. Oh shit, we don't actually have this yet because we're not an object yet. Vector JSON. No, vector profile node. Non-null ref footer vector profile node. Roots. This is what we're going to pass to the object we're creating. So we want one of these. Vector profile non-null ref footer vector. Okay. Then auto find or create root. This will just be like this, and then it takes a string symbol and a U32 address. And does vector have a first matching? No, we can't search a vector like that. So, I mean, we have find, but it's not really what I want. Do we even have find? We have find. But it doesn't work the way I want it to. So we'll just search it manually. If if root symbol is same as symbol. Let's compare. Let's compare integers before we compare strings. Then we have found it. Return root. Like that. We'll say this returns a profile node. If we don't find it, then auto new root is profile node, create, symbol, address, roots, append, move, new, root. Oh, we don't need to move actually. Return new root, dot footer. Okay, so, wait, why does that as U32 returns int? Well, that's clearly not right, Andreas. Wait, why do all of these return int? What's this hilariously stupid mistake? Okay, well, that's my bad. I don't know what was up with that. It's a nice little JSON bug fix there. Okay, so now we have if we didn't have a node, then we do have a node. But if we already had a node, we gotta insert ourselves as a child of this node. Because we're gonna we're iterating the stack one frame at a time, right? So we always want to be inserting ourselves into the parent. So we gotta find the insertion point in the current node. So node is node find or create child symbol address. And then this is going to be extremely similar to this, except it will be in profile node. And this could actually return profile node amp, because it never returns null. Okay. This is mroots. Oh, no, sorry. mchildren. My goodness. And this one is new child. What are we screwing up here? We're probably okay. Profile model. Incomplete class. Well, that's my bad, I guess. We have a destructor of something. Let's just move the destructor out of line. Profile. Oh wait, it is out of line. Public G model. I'm gonna steal maybe the DOM tree model from the from libHTML. It's pretty close to what I'm looking for. In that we have our own little tree that we want to represent in a model. DOM tree model, profile model, search and replace. Boom. Okay, and we need to provide a profile. We'll just say class profile. All of this stuff can be out of line. We'll just want to define the class, you know? Am I not including profile model here? I guess I'm not. Okay, well that totally built. So let's see about this now. So now we've found either a new route to put it in. In that case, we're basically fine until next iteration. Continue. Otherwise, find or create child at the current node. And then we'll just keep going like this. Oh, so maybe this is all we need. Maybe this is all we need. Maybe I'm blind, but we'll see. Okay, so then let's look at profile model. Let's get the DOM tree model. We'll just copy it into profile model. Ploop. And now comes the part where we actually change everything. Profile. DOM tree model is now a profile model. And document becomes profile. Then everything else is going to be different, so we have to deal with that. But maybe we can have some icon actually for these functions. We'll just use the inspector object. That's the generic. We'll just call it the frame icon or whatever. Footer graphics bitmap and frame icon. Oh, they're G icons. Oh, that's my bad. G icon. Profile. So now we have to, let's try to get rid of some of this code first. So we're always going to use the frame icon. That part is easy. Our node type is not the DOM node, but rather profile node star. So we can just fix that up. And we don't have such a thing as text nodes. Everything is the same. So the thing that we want to display for each thing is just going to be, let's just do the symbol at the moment. Can do the address thing separately. In fact, this can just be node symbol for now. We don't need white space collapsing, that's HTML specific stuff. And then right now we're not going to see like how many samples were in each thing, like how many samples were in each frame, but I think that's okay. Right now we just want to build up the tree. So child count. So children. Oh, I guess we can implement the child count function. Let's see, child count, children size. Okay, and then, oh, they needed their parent, right? We have the parent right here. So profile node, parent, return parent. And document. So here we always have, in the DOM tree model, we always have only one root. But here there can be multiple roots. Shit, I didn't take that into account. What is happening here? We're walking the children. First child, next sibling. Maybe this is more like the remote object graph model, now that I think about it. It's a lot more like this thing. This thing has multiple roots and everything. I'll show you this. Oh, shit. Can we just get this to build? So we have the inspector program that allows you to connect to a running process and just see what it's doing. So we'll get the taskbar. Oh, we don't have grep. We have fgrep. So we have inspector 11. And this here is the remote object graph model. These are the objects in the taskbar process, and we can actually look at them. You can see here's the window, here's the frame inside it, here's the 3 buttons, it's these 3 right here, and the taskbar buttons and so on. Very, very handy little program. And this tree model here, we're just going to steal it because it supports multiple roots and the DOM tree model does not. So remote object graph model. Should have stolen that from the beginning. It's important to steal the right thing from yourself. Profile model. Profile. And profile. Okay, and then this one was called frame icon. All right, gotta tweak the little things again here. So M process is M profile. Loop and remote object is profile node. Loop. No, maybe we could have some kind of a generic tree model thing. I don't know. Because this is evidently kind of useful, so we could probably do better. Parent and profile. We don't have a way to get to the roots. How do we get to the roots? Oh, they're just not exposed. Oh, sure, yeah. Let's just expose them. It's not a big deal. Okay, And children, can't get to the children either. Profile. No referer vector profile. Okay, parent. And I guess the main difference between these two things is that the other guy, he was unashamedly using structs for everything, and I made a class for this. Other than that, everything is basically the same, just that I have to call getters here. Frame icon. And remote object symbol. Just going to call these node. And we have made CubeCreator willing to not complain about syntax. So let's boot this up and see what we get. PV, pbrush prof. We got nothing because I didn't add a tree view or anything. Dang it. Got a little ahead of myself there. Tree view is gTreeView construct no parent and then tree view set model profile model window set main widget tree view. Will this work? No profile model. Oh. We gotta implement that. Gmod. Crap. Where did we die? Profile model. We never construct the model. I'm very silly today. Profile model, create this. Okay, so I see the start of something, and look at this. We are drilling into the stacks right here. So we don't know how heavy each one of these are. And we got some garbage here. I think we should probably ignore empty ones. Let's see, how do we do that? Maybe where we parse the profile. If we get a frame that doesn't have a symbol, we can just skip that one. We'll stop there, actually. So we'll say if symbol is empty, break. Wonder what this gray square here is. I think it's scroll bar related. Should fix that at some point. Anyway, okay, so we don't know how many samples are in each one, but these are our leaf stacks right here. Wow, this one is really, really deep. All the way down in opening a file. It was loading a font. It's kind of interesting. You can go all the way here. Wonder what it was doing at this time. See, this graph isn't rendering quite right. It's probably because we not doing the right thing in the parent thingy in the profile model. But that's not the thing I want to brain about at the moment. So I guess the thing that would make this super interesting is if we could see how much time was spent in each one of these. So basically, or just how many samples were at each point. So we could make this a lot better if we got rid of this offset here. The offset is stupid. So since this is what the profile looks like at the moment, let's just live with it and fix it up. So we'll say only symbol without offset is, or hold on, parts. We might have spaces in the symbol name, but we only have a plus at the end. Okay, maybe this whole thing is so stupid, or we can just fix it in the kernel. Profiling, where did we do this? This is where we print that out. Symbol string slot. I think we'll just save the offset instead. Symbolicate stack. Oh, or it comes from in here, the L floater. So this guy is gonna have to know how to export offset. We'll do something like this. Oops, excuse me. Address minus symbol address. So, oops, in the case where we have an out param, we'll just return demangle directly like this, and symbolicate. We'll make this an optional thing. Like that. You can get the offset if you want. Okay. And then here we will use that to get the offset. So unsigned offset, or U32 rather. Symbolicate offset, and or no, even will even be like this. U32 offset slot is stack offsets I++. And we'll store it like that. Offset slot is this. Okay, blah, blah, blah. 32 offsets. X stack frame count. Okay. Maybe this will work. Proc.fs. Then when we print out the profile, we'll add the offset to each frame. And then we don't have to deal with this in the viewer, and we don't have to think about this again. Okay. So we'll have to make a new profile, but it will be okay, because it'll be better. PB. And let's see, PS. Where are you, paintbrush? Right here. 17. Profile, 17 on. Okay, oh, let's draw something. Green. A little bit of bucket fill in blue. Okay. And we totally crashed. That was not good. Why did this go so wrong? Offsets, those are just U32s. String slots, symbolicate. How to offset. What went wrong here? Lots of crashiness, but what was the first thing? Audio server. Everybody just starts to hurt. Okay, wait, let's see what kind of commits we have here. We have JSON value fixes, so let's just commit those. JSON value fixed wrong return type of as A30 U32 and friends. And file system, or no, these are not independent changes. This here looks really weird. Why is this? Like that. But that doesn't fix my problem. It was just weird. Let's just make a very short profile and see what's up. Who do we profile? CPU graph. On. Off. Seems fine so far. Off profile. There we died. Serializer. Why are you falling apart so badly? Jeez. Symbol string slot. Demanual returns a string. Is it confused about the type of this somehow? Frames by am I doing something really dumb here, like that I'm just not getting? I'll just say offset 0, and then stack offsets. I don't understand what is going wrong. Andreas, why don't you understand? What are you even trying to fix here? Okay. What if we don't add the offset then? Is this changing the layout of my profiling stacks somehow too badly? The samples, I mean? So it's still broken. And I assume that I have messed it up in symbolication somehow, but presumably we're going here every time. Let's just say set out. I don't know, I just want to find out what the heck's going on. So is this destructive? What if you just don't write out? Then what would happen? Okay, so these things are overwriting something that we don't want to overwrite. But how? How am I managing to misuse this? How am I being a dumbass with it? I don't get it. Offset slot is what? Stack offsets I++. What are we saving the frame then? Wait, stack frames I. Oh. Oh. Oh my god. I'm incrementing I twice. Oh, all right. Well, that's stupid deluxe. Good gosh. All right. Sell down Andreas. Proc profile. JP. Now we have our offsets. Okay, now we can get back to what we wanted to do. Holy moly, that was a stupid little session. Thank you to everyone who noticed that 10 minutes ago and have been waiting for me to realize. For hanging out. Let's, oh right, we want to make a new profile now. So let's get paintbrush up on screen. And profile. Paintbrush is 16. And let's get some of those bucket fills up in here. All right, off. And cat proc profile. pbrush.prof. Call it pbrush 2. And there we go. Mount. Home on pbrush 2. We'll just call this the new pbrush. U-mount, and okay, now this means that we'll have the offset here as well. So get the offset, and we can just ignore the offset for the time being. I think that's okay, because this whole thing is about accumulating things. So this is step 1. So now we have 2 roots apparently, 1 main and 1 start that calls main. Wait, how do I open this guy? Wonder if this is because the stack is so deep that we hit the limit. Probably, actually. Oof. It's a deep stack right here. So that's one thing that will give us multiple roots if we go really deep. So now these are identical, but they have different addresses still. That's why they show up multiple times. So we have to disambiguate on the symbol only. I think we'll do that. Okay. Okay, and no, that was not good enough. Wait, why was that not good enough? The symbols are identical, then return the root. But when it comes to find or create child, these should be called child also. I guess we should add offset here. Even though I don't particularly super care about the offset at the moment, it'll still be interesting in the future. It might be interesting in the future. I don't even know yet, but we'll stash it away. why did they not, why does it not collapse all of them into one? That's what I want to know. Wait, am I rebuilding the... I'm just rebuilding the kernel. Okay, making a lot of silly mistakes today, but we keep catching them, so it's okay. Okay, so what do we have now? Okay, so now this is looking a bit more sane. No multiple execs, we go into pump, then these are the different places where we go from there. Got some samples here in the destructor multi-paint event. That's probably just a one sample. So this is what we want to get next, is figure out how many samples in each one. And the easiest way to do that is to just keep a counter on the node. So whenever we find one and use it again, we'll just bump this counter. We'll call this samples. Samples here. Or just samples. Samples sounds like it's going to give you a bunch of samples. Maybe we'll call it sample count. U32 sample count. Const return and sample count. Okay. And find or create child. Well, we'll just have something here like what? Increment sample count. And we'll do that right here. Increment sample count. And we should probably show the sample count somewhere. In the profile model, we will add it to the display, I think. So do something like show the sample count in a little, just a number next to the symbol, like that. I think that could be pretty good for a start. Okay, so now we can see we have 251 samples in the start. 251, and here we start to diverge. So still we have most of the samples here, so now we can just follow whoever has the most samples, we'll just follow him. And I think it's an accident that these are sorted. But yeah, this is pretty cool. So we can actually, we should make this sort somehow. That would be really, really cool. I guess we can do that by sorting the children of each profile node. After we're finished, we'll just go through and sort them. So we can see here that Painter Blit has most of these samples. Damn, this is going to be so freaking awesome. Paint event, dispatch event. And we end up in Blit. A lot of time spent in Blit. I guess that's to be expected, given that this is a paint application. It's pretty logical that we Blit a bunch. And here we are in malloc, which calls the kernel, which calls mmap right in the kernel, creating a string. It's for the name of the mapping. Seems a bit expensive. Maybe we could do less of that, but it's not the end of the world, actually. Allocating the region for the memory is heavier. Damn. This is so interesting. Okay, let's sort it so that it's even better. So profile model. So after we generate the profile tree in profile, then we'll do a pass over the tree and sort everyone's children. It's going to be fine because sort order doesn't matter for the tree integrity because everything is heap pointers anyway. So Let's see. For auto roots sort children. Does this make sense? I think this would be okay. And then in profile H, we'll just add a function, an add a line function, I guess. Sort children. And profile node sort children. Maybe we can use ack quick sort for this. Children begin, children end. And we just need a little lambda that gets to compare two children, tell you which one is less, if A is less than B, that's all we need to answer. So 8 is a profile node. So if A.sampleCount is less than B.sampleCount, although I guess now we'll get ascending sort order, if I'm not mistaken. And we don't sort the roots, actually. Oh no, this is what we wanted. Oh no, wait, it's not sorted at all. You jerk. Wait, did I not build again? No, I built. Oh, but we don't recurse. Ah, no. Sort my children, and then for auto child children. Child sort children. You sort your children too. All right. This did not work out. Sort children. Why am I not allowed to do this? I'm trying to swap two profile nodes. Ooh, swapping on a non-null ref putter vector makes everybody sad, I see. Yeah, we're not really equipped to handle that. Shit. Okay, we're gonna have to use a regular vector of non-null ref putter for now. Non-null ref putter vector is great, but it has some shortcomings. The fact that when you iterate over it, it gives you t-amp rather than t-star, and it creates some problems for generic algorithms because it will, because quicksort will try to swap. I'll show you. Quicksort will, it's just a standard quicksort that will swap as it iterates across the container, or the range, really. But because what the iterator gives us is t-amp, it's going to swap the value types with each other in the case of non-null ref putter vector. So non-null ref putter vector, the point of it is to give you t-amp so that it's pleasant to work with, because you can use dots and everything and you don't have to use arrow operator. But in this specific case, swap doesn't work. So I'm not even really sure what's the solution for this. I guess we would need some kind of some specialization somewhere of something that knows how to deal with non-null ref putter vector when it comes to sorting or when it comes to swapping. Maybe it could hand out references to some intermediate type. I'm not sure. But for now, we are going to have to fall back to using some arrows. Maybe not so many though, just a few. Makes me sad to use arrows. but it is what it is. I would rather have something that works than not something that works. Something that not works. Sample count. Wait, what am I doing wrong? Node dot. Okay. It's good to find some design problems with the ACK types, especially non-null ref footer vector, because it's a pretty new thing. Okay, so this did not go so well either. I'm guessing that it was probably screwed up by the sorting. I'm guessing, but let's just not sort and see what happens. No, it didn't break into sort, it broke somewhere else. So where are we going wrong then? Profile model data. Profile node. So I'm gonna not fall. What is the trap that I always fall into with this shit? I'm putting the wrong thing in the internal data. Is that it? So where do I create the internal data of this profile model? An index. Because the thing is that this takes void star. So whatever you pass him, he'll accept it. No questions asked. So here, we are giving it the address of, I think this is it. We're giving it the address of a non-null ref footer rather than the profile node itself. I remembered, I've fallen into this stupid trap twice. So, oh, it's probably the same with roots actually. No, well, it should be the same. But we can do that one separately, but or no, actually we can't fix that one that way. But this one should be done that way. Okay. Okay, I don't know what I did wrong there, so let's just try that again. Okay, now can we please see some sorted contents? Yes, we got ascending sort order. So that's an easy fix. We just gotta lie about less than. Say, well, are you the complete opposite of less than? PV. Should make the window bigger by default. Okay, look at this pupper right here. We are sorting by sample count. This is starting to look like a regular, proper profile. My stoked levels are rising as we speak. Look at him go. He's sending a message to the Windows server. How cool is that? Deref if not null. So sending this message spends a bunch of time freeing byte buffers. I guess that's the byte buffer where we serialize the message before we send it. We could probably reuse the same buffer every time. Might be an interesting optimization. Or at least have some kind of a scratch buffer, you know? Yeah, and then allocating byte buffers. So communicating with the Windows server is probably pretty allocation heavy. I haven't looked at that before, so that's interesting. Current setting the backing. I mean, we're looking at the tiny things here. Let's look at the bigger ones. So blit, that's a leaf right here. So just blitting. It's pretty heavy. And what else was heavy in here? Dispatch event. Dispatch event. So mouse down. What are we doing in there? Bucket tool. Oh, it's the bucket fill in the paintbrush app. It does a flood fill algorithm using a queue class that I wrote specifically for the bucket fill. And I think there are probably way smarter bucket fills than I implemented. I just did I didn't read about how to do efficient bucket fill. I just did something that made sense to me. So can definitely optimize that. But it's not that many samples. So actually, we know that how many samples these are. These are like milliseconds, actually. Because we sample every millisecond. But, so it's not like we're looking at something horrendous here. But damn if this is not awesome. So cool. I guess if we have multiple threads, we should probably put them in separate roots as well. So maybe the threads should be the root thing, actually. But we don't have to deal with that today. I think we've done plenty here. This is just too interesting. So let's generate a new profile of something and see how that works out. I definitely want to make a profile of loading some stuff over the web, because I've been very curious what's up with that. And I have this little test page, happy birthday test page of Serenity. So we are going to profile the protocol server while we load. So profile 19 on. All right, open up. Just gonna look here for this thing to reach no pending resources. Will this work? Did we crash? Oh, it's all of this. I gotta get rid of that. Writing offset too. It's gonna do this once for every sample. Can I make this speed up by not seeing it somehow? Yes. Out of memory. Shit. Kernel panic. Dang it. All right. Let's try it one more time. Put that thing not there. Maybe we can get a little faster profile. We don't have to profile the whole time. Yes, protocol server is not loaded. That makes sense, because it loads on demand. So now it's up. So profile 18 on. And we'll just load some resources and we'll stop the profile. And was that too much? Nope, finished. Okay, let's close it. Proc profile. Protocol server.prof. Shit, we died. Oh. So many problems. K-buffers, they pre-allocate a certain amount of space, and I've never hit that limit ever before. But when we create a K-buffer, we allocate how much? Oh, maybe it's K-buffer builder that I'm thinking of. Yeah. K-buffer builder allocates 1 megabyte, and that was not enough. Shit. But I still want to see what this is about. So let's just do 4 megabytes then. Can't stop now, I'm so close. Okay, so hit me with the browser, PS, profile, and let's profile the frickin' protocol server on, and I'll just stop it. Oh shit, stop it right here. Proc profile PS prof. Okay, we got it. And how big is this exactly? PS prof. Well, it's a little over a meg. It's not so bad. Now let's look at that puppy. Okay, this is our protocol server. Over 1,000 samples. What are you doing, protocol server? Most of the time in on-socket connected Lambda. It's fine. And then we're calling. It's a fair amount of time just creating debug streams, I have to say. Wow, look at this. That's so much time in debug streaming, actually. Could probably look at optimizing that. What is the time spent on? Oh, that's curious. So we're just in the syscall trap, and I guess we get interrupted here. That's kind of strange. But whatever. Okay, so clearly we were spending a lot of time in the, creating a debug stream. It's called trap entry once again. I wonder if we could make our traps a bit tighter. So here, reading from a socket, receiving from IPv4. This is taking a packet from the packet queue. And look at this. Most of the time in receiving is spent in freeing k-buffers. That's very interesting. Non-null ref footer to k-buffer. What does it do? K-buffer impl, sorry. So we're calling the destructor of this guy. Where are you, destructor? I guess it's not here. Oh, it's just a default destructor. So internally this thing has a non-null onputter to region. So we'll call the region destructor. I guess I would have expected to see more of this. Oh, but we're not going to see this because it disables interrupts here, which means that the sampler can never actually... Oh, that's so interesting. And kind of obvious when you think about it. So when we disable interrupts, the profiler can never catch you. So we'll never see anything that happens while interrupts are disabled. Perfectly logical. So here, this will free a memory region, which is an interrupt disabled operation. So this is the edge of our profiler vision. So cool. This is so freaking cool. Damn. All right. So freeing regions, extremely expensive, extremely heavy. And every packet that we receive is in a region, so we could definitely optimize a lot here by reusing packet buffers, for example, because this is all inside the kernel. When we get the receive from, or we get a read syscall, we just want to copy something from the kernel to user space, and we don't really. We can store it any way we want in the kernel. We just happen to use separate page allocations at the moment via the kbuffer API because kbuffer is really convenient. Anyway, super interesting. What else can we find? Here, CIO device, read. Spent some amount of time allocating a buffer to read into, I suppose, which makes us call mmap a lot. Presumably because this buffer ends up pretty big. So we have to mmap, then we have to create anonymous VM objects, and then I guess Probably here we are disabling interrupts and we don't get to sample once again. Very, very interesting. Did we have something else heavy down here? This is, I suppose this is when we send something to the, we send our HTTP request. kprintf, half the time spent in kprintf, and the other half in TCP socket send outgoing packets. Look at all this stuff. So fascinating. It's kind of an interesting incentive also to try to do, try to avoid disabling interrupts as much as possible, because it will like make your profile richer, because you will be able to see more things that are happening. Right now we're kind of being a bit gratuitous with disabling interrupts quite often, using it in place of more sophisticated, finer grained locks. We're just using the interrupt flag as like, lock everything, and could do better. Finish up HTTP job. What happens in there? We're just freeing byte buffers. Freeing is expensive because, again, we unmap, and this ends up destroying a region which we can't see because interrupts get disabled. Byte buffer, same. Freeing is very heavy. Need to look into that. Read line, allocating, appending, which is more allocating. Okay, I'm guessing that malloc is pretty heavy. Every time that it ends up calling mmap, it's going to be pretty heavy. And especially for bigger allocations, mmap will always, malloc will always mmap anything that's bigger than like a page at the moment. So anything bigger than 4 kilobytes will go directly to mmap. Anyway, now we're just doing profiling here. But this will be super, super awesome. We can do some serious profile analysis and optimization based on this type of stuff in the future. I so love this stuff. I spent years profiling and optimizing based on profiles. So now we are entering into one of my favorite wheelhouses. Okay, I gotta stop, because if I don't stop myself, I'll just sit here forever and stare at profiles. So, let's commit some stuff. So let's see, procfs, and let's get rid of that kbuffer builder change. Or maybe we can live with that change, actually. It's not the end of the world, because kbuffers are, kbuffer builder is lazily allocated anyway. And it just, we end up costing the VM, but we don't cost the physical pages, because even though we make pre-allocate 4 megabytes now for each kbuffer, that's just virtual memory. We're not actually committing any physical pages to it until you try to write into that memory. So that's pretty okay. But let's commit that. Kernel bump kbuffer builder VM allocation to 4 MB. This is pretty large, but since it's not eagerly committed to physical pages, it's probably okay. Bumping after hitting some hitting some space, after running out of space for my for a protocol server profile run. Okay. Then what do we have? We have all this change right here. So we'll add the offsets. Kernel, separate out the offsets symbol offsets in profile output. Instead of saying main plus 39 and main plus 7 etc. We now have a separate field in for the offset into the symbol. Great. Let's make that thing a little bigger by default. It's irritatingly small. Set rect. My favorite rect in the world. It's not the divine interrect, but it is a good rect nonetheless. So I think we'll add it here at this point. Make file, make all, add load root, commit. Profile viewer. Begin work on a visualization tool. Profiles. This is a we begin with a simple tree view that shows a recorded profile. To create profile, simply do this. One. Or no, let's do that. Profile, PID on. Wait while PID does something interesting. Profile PID off. Cat proc profile. My profile dot prof. Profile viewer. My profile dot prof. To create, to record and view a profile. Process with PID. Oh, the hash mark or hashtag or pound sign or whatever, I can't use that and get commits because it will look like a comment and disappear. So we'll save this way instead. Okay, super duper cool. Now I kind of wish that, or I really quite wish that I would be able to have multiple columns in this tree view, because right now tree views can't have multiple columns. It would be nice if we could show the sample count actually to the left of this. So you would have only one column with a tree in it, and then you would have other columns that have sample counts. But this is okay for now. It's just something that we should make better. But dude, I'm super happy with this. So I think this is going to be the end of today's video. So if you made it this far, then I thank you for watching and for hanging out, coming back and all that. And I really appreciate all the interest lately. It's really cool to have company. And welcome to all the new people once again. I hope you like it here. We do a lot of fun stuff. And everyone's obviously welcome to participate, whether it's, you know, in comments or in programming. The system is open on GitHub if you want to work on it or just mess around. So yeah, I hope you all have a great day, and I will see you next time. Bye.